I need you to stay with me for the next few minutes and hear something that most science communication never quite manages to convey with the clarity and the seriousness it deserves. Because the multiverse is not a fringe idea. It is not the speculation of imaginative but unserious thinkers on the edges of physics. It is the conclusion that falls out of our most successful, most rigorously tested, most precisely verified scientific theories when you follow the mathematics all the way to the end without flinching. The equations do not suggest the multiverse as a possibility. They insist on it. And the evidence, our real, observable, measurable evidence, is hiding in places that most people have never thought to look. Today we are going to look, all the way, without flinching. And by the time we are done, I think the question you will be asking is not whether the multiverse is real. It will be why nobody told you the evidence was this compelling this whole time. Let us begin with the most important thing to understand about evidence in modern physics, because this is the context that makes everything that follows make sense. In everyday life, we think of evidence as something direct. You see the thing, you touch the thing, you measure the thing directly. But in physics, the most important evidence has almost never been direct. It has been inferential. We have never seen an electron. We have never directly observed a quark. We have never watched a gravitational wave in real time the way you watch a wave in the ocean. What we have done is built theories, derived predictions from those theories, tested those predictions against measurements of observable reality with extraordinary precision, and when the predictions match the measurements, when the theory tells us the electron will behave in a specific measurable way, and then the electron behaves in exactly that way to 12 decimal places of precision, we conclude that the theory is describing something real even if we cannot observe that something directly. This is how science actually works at the frontier. And it is by exactly this standard, the standard of precise theoretical prediction confirmed by precise measurement, that the evidence for the multiverse needs to be understood and evaluated. Not by whether we can see another universe directly, by whether our best theories, confirmed to extraordinary precision by experiment, lead necessarily to the conclusion that other universes exist. And they do, in multiple independent ways that have nothing to do with each other and everything to do with the underlying structure of reality. The first and perhaps most immediately striking piece of evidence comes from the cosmic microwave background radiation. The faint glow of thermal radiation that fills the entire universe, the afterglow of the Big Bang itself. Detectable in every direction, we point our instruments and carrying within its temperature variations an extraordinarily detailed map of the universe as it was just 380,000 years after the moment of creation. This radiation has been measured with breathtaking precision by a series of space missions, most recently and most precisely by the Planck light, which mapped temperature variations in the cosmic microwave background to an accuracy that would have seemed impossible just decades ago. And within that extraordinarily detailed map, there are anomalies. Features that the standard model of cosmology, our best, most tested description of how the universe evolved from the Big Bang, does not predict and cannot fully explain within the framework of a single isolated universe. The most striking of these anomalies is what cosmologists call the cold spot, a region of the cosmic microwave background that is significantly colder than the statistical models predict. Large, clearly defined, and located in the southern hemisphere of the sky in the constellation Eridanus. Within a single universe framework, the cold spot is anomalous. It is the kind of feature that should not be there at the level of statistical significance it displays. But within the framework of bubble universe theory, the model arising from eternal inflation that describes our universe as one bubble in an infinite sea of bubble universes, the cold spot is precisely what you would expect to see if our bubble universe had, in the very early moments of its existence, collided with another bubble universe. The collision would have left exactly this kind of thermal imprint in the cosmic microwave background, a cold, clearly defined region. In exactly the location and with exactly the characteristics we observe. This is not proven. The cold spot has other potential explanations within standard cosmology, and the scientific debate continues actively. But the point is this: the bubble universe collision hypothesis predicted what kind of evidence such a collision would leave before the Planck satellite measured the cold spot with sufficient precision to make the comparison meaningful. The prediction preceded the precise measurement. That is exactly the structure of legitimate scientific evidence. The second piece of evidence is more subtle and in some ways more profound because it does not come from cosmology at all. It comes from quantum mechanics, the physics of the smallest scales, and it has been staring at physicists for nearly a century without being fully accepted for the simple reason that its implications are too extraordinary for most people to sit comfortably with. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions have been verified to accuracies of 1 part in 10 billion. There is no theory in any field of human knowledge that has been tested more rigorously or confirmed more decisively. And quantum mechanics describes something at the heart of reality that has no satisfying explanation within the framework of a single universe, something called quantum superposition. A quantum particle, an electron, a photon, any entity at the quantum scale does not have a definite position, a definite momentum, a definite spin, or a definite state of any measurable property until it is observed. Before observation, it exists in a superposition, a simultaneous combination of all possible states weighted by the probability of each. When you observe it, it appears to choose one state. The superposition collapses, you see one definite outcome. But here is the question that has haunted physics since the 1920s and that the many worlds interpretation answers in the only fully consistent way anyone has ever proposed. What happens to all the other states, all the other possible outcomes that the superposition contained? Where do they go when the observation selects one? The Copenhagen interpretation, the standard answer taught in most physics courses, says they simply cease to exist, the superposition collapses. The unchosen possibilities vanish, but this answer has a deep and unresolved problem. The equations of quantum mechanics do not describe collapse. They describe the superposition evolving continuously, branching, encompassing more and more of the universe in its quantum correlations. Collapse is added by hand, an ad hoc rule appended to the theory to make it match what observers experience without any equation describing when or how or why it happens. Hugh Everett's many worlds interpretation, proposed in 1957 and now taken seriously by a significant fraction of the world's leading theoretical physicists, removes the collapse entirely. In Everett's formulation, the equations of quantum mechanics are taken completely literally. When a quantum superposition interacts with a measuring device, the measuring device enters into superposition. When that interaction encompasses an observer, the observer enters into superposition. The universe itself branches. Every possible outcome of every quantum interaction occurs in a different branch of a universal wave function that contains all of them simultaneously. The evidence for this interpretation is not a direct observation of another branch. By definition, such an observation is impossible since the branches do not interact after the splitting. The evidence is that it is the only interpretation of quantum mechanics that takes the theory completely seriously without adding anything extra that the theory itself does not describe. It is, in the language of physics, the minimal interpretation. And the experiments that have tested quantum mechanics most precisely, the Bell inequality tests, the delayed choice quantum erasure experiments, the quantum erasure experiments, all consistently confirm the quantum mechanical description to extraordinary precision, a description that, taken at face value and without modification, describes a universe that is constantly branching into parallel realities. The third line of evidence comes from inflation, the theory describing the extraordinarily rapid expansion of the universe in the first tiny fraction of a second after the Big Bang. Inflation was proposed in 1980 by Alan Guth specifically to explain three deep puzzles in cosmology that the standard Big Bang model could not address. The flatness of the universe, the uniformity of the cosmic microwave background across regions that could never have been in causal contact, and the absence of magnetic monopoles that the standard model predicted should be abundant. Inflation solved all three puzzles simultaneously, and the specific predictions it made about the statistical properties of the cosmic microwave background have been confirmed by subsequent measurements to remarkable precision. But inflation, taken seriously as a physical description of the early universe, does not just solve those three puzzles. It creates something that its original proponents did not fully anticipate, something called eternal inflation. The quantum field that drives inflation does not switch off cleanly everywhere at once. Quantum fluctuations mean that while inflation ends in some regions, creating bubble universes like our own, it continues elsewhere, perpetually driven by those same quantum fluctuations that are inherent in the physics and that no mechanism can remove. The result is an eternally inflating background that continuously nucleates new bubble universes, each with its own physical properties determined by the specific way inflation ended in that region. This is not an additional assumption layered on top of inflation. It is what inflation predicts when its quantum mechanical implications are taken seriously. André Linde, one of the architects of inflationary theory, has described eternal inflation and the resulting multiverse as essentially inevitable given the physics of the inflationary field. The multiverse is not inflation's speculation, it is inflation's prediction. And inflation itself is supported by some of the most precise cosmological measurements ever made. The fourth piece of evidence is perhaps the strangest and the most philosophical, but it is taken seriously by physicists of the caliber of Max Tegmark at MIT and Roger Penrose at Oxford. And it addresses a question that sits at the very boundary between physics and mathematics. The question is this: why does the universe follow mathematical laws at all? This question sounds almost trivially simple until you sit with it seriously. There is no logical necessity for the universe to be describable by mathematics. There is no reason that physical reality should conform to equations. And yet it does, with a precision and a consistency and a depth that goes far beyond anything that would be necessary if mathematics were merely a useful approximation. The physicist Eugene Weiner famously called this the unreasonable effectiveness of mathematics in the natural sciences, the mysterious fact that abstract mathematical structures developed with no physical application in mind consistently turn out to describe physical reality with extraordinary accuracy. Max Tegmark's mathematical universe hypothesis proposes that the explanation for this mystery is that physical reality and mathematical reality are the same thing. Every mathematically consistent structure does not merely describe a possible universe, it is a universe in precisely the same sense that our universe is real. We inhabit one mathematical structure among an infinite landscape of mathematical structures, all equally real, all existing in the same sense that we exist. The evidence for this position is not experimental in the conventional sense. It is explanatory. It dissolves the mystery of mathematics' unreasonable effectiveness by making that effectiveness not just unsurprising, but inevitable. And in physics, a theory that explains away a deep mystery without creating new ones is taken very seriously regardless of whether its implications are comfortable. There is one more piece of evidence that deserves serious attention, and it is one that most popular accounts of the multiverse overlook entirely: the fine-tuning of the fundamental constants of physics. The universe as we observe it depends on a set of physical constants: the strength of gravity, the mass of the electron, the value of the cosmological constant, the strengths of the fundamental forces, that are calibrated with extraordinary precision to values that permit the existence of complex structures like atoms, molecules, stars, planets, and ultimately life. The cosmological constant, the energy density of empty space, is perhaps the most dramatic example. Its observed value is smaller than the value predicted by quantum field theory by a factor of approximately 10 to the power of 120. This is not a small discrepancy. It is the largest discrepancy between theoretical prediction and observation in the history of science. If the cosmological constant were even slightly larger than its observed value, the universe would have expanded so rapidly after the Big Bang that no structures of any kind could have formed. No galaxies, no stars, no planets, no life. Nothing but a rapidly expanding void. Within a single universe, this extraordinary fine-tuning has no satisfying explanation. It appears to demand either a designer or a staggering coincidence, neither of which is scientifically satisfying. But within a multiverse containing an enormous number of universes with different values of the fundamental constants, fine-tuning requires no explanation at all. Most universes have constants incompatible with complexity. In those universes, there is no one to notice. In the rare universes where the constants fall within the narrow range permitting complexity, observers evolve and note, as we do, that the constants appear extraordinarily well-tuned. The appearance of fine-tuning is simply a selection effect. We are here to observe the constants because only in universes with these constants does anyone exist to observe anything. This argument, the anthropic principle applied to a multiverse, was first made seriously by physicist Steven Weinberg in 1987 before the accelerating expansion of the universe was observed. Weinberg used it to predict that the cosmological constant would be found to be small but non-zero. In 1998, observations of distant supernovae confirmed that the universe's expansion is indeed accelerating, driven by a small, positive cosmological constant, exactly as Weinberg's multiverse-based reasoning predicted. A prediction made 11 years before the observation it anticipated. I want to be completely honest with you as we close, because honesty is the only thing worth offering when the subject is something this important and this extraordinary. The multiverse is not proven. It may never be proven in the direct, observational sense that we prove things in everyday science. The other universes, by their nature, may be forever beyond our ability to observe directly. Some physicists argue that this places the multiverse outside the domain of science entirely, that an unfalsifiable theory is not a scientific theory regardless of how elegant its mathematics. But here is what cannot be argued away. Our best theories, quantum mechanics, inflation, the mathematical structure of physical law. Theories confirmed to extraordinary precision by experiment, theories that have earned their right to be taken seriously by their track record of successful prediction, lead necessarily and repeatedly to the conclusion that our universe is not alone. The multiverse does not appear in these theories as a speculation or an add-on or a philosophical luxury. It appears as a consequence, as what the mathematics demands when you follow it honestly to the end. And perhaps that is the most extraordinary thing of all. Not that the multiverse might exist, but that the universe we live in, this one, the one you are sitting in right now, the one that produced stars and planets and chemistry and life and human beings curious enough to ask these questions, this universe follows laws that point insistently beyond themselves, laws that refuse to be contained within a single cosmos. Laws that keep opening outward into something larger and stranger and more magnificent than any single universe could ever be. The equations are trying to tell us something. We owe it to ourselves to listen. If this changed something in the way you see reality out, hit that like button, subscribe to the channel, and share this with someone whose mind is ready to be expanded. Tell me in the comments which piece of evidence hit you hardest. I read every single reply. See you next week for something even deeper.